Okay, last concept of momentum. And it's taking the idea of conservation of momentum and applying it to angular momentum. Okay, so before we discussed how angular momentum is the angular inertia, which we call moment of inertia, multiplied by the angular velocity. And so we, again, in a similar situation, whatever angular momentum we start with, whatever our angular momentum initial is, within a closed system, it has to be the same for the final. Okay, and we know that we can add in, replace the initial conditions for what they equal, right? So initially, our angular momentum would be moment of inertia minus angular velocity initial, and that's going to equal our moment of inertia final multiplied by the angular velocity final, okay? So here's another way of viewing that idea of the skater bringing her arms in and spinning faster. We know that if we bring mass of the object closer to the point of rotation, that it reduces our angular inertia or moment of inertia, and it becomes easier to spin, right? And so when we do that, if our moment of inertia is large, and that would make our angular velocity small, but these have to be equal to each other. So if this now becomes small because we brought our arms in, then our angular velocity must increase in order for these to be equal to one another. Okay? And so that's the idea. It's just saying, like, we're applying the exact same concept, we're just plugging numbers in. We're saying that we originally started at 3.74 rads per second, rotations per second, and then through a manipulation of this, we were able to calculate, given our moments of inertia, that when we bring our arms in and we reduce the moment of inertia, that our angular velocity will increase. Okay? Now, because our linear velocity is always changing, which means that there's always an acceleration, we can observe some interesting phenomenon from this. And so if you have like a bike tire and it's spinning, that spinning bike tire has an angular velocity, right? And it also has a moment of inertia, as angular inertia, and we talked about using the right hand rule to show that the momentum is going up, right? If you then exert a torque onto this wheel, meaning that you turn it around, right? You cause rotation of that wheel, then an equal and opposite torque will react on you. And this is really interesting to see because it's like saying, we know how we said that force is analog to torque for rotational motion. And we know from Newton's third law that if we apply a force, like if I push down on the table, the force of the table is pushing back up on me, right? And so if we exert a torque on the wheel, then the wheel will actually exert a torque back on us. And so if we're on like a rotation table or something, frictionless, then the person actually starts spinning. That's how some gyroscopes and other things work. Okay, so just make sure you have a conceptual idea of conservation of angular momentum. Primarily, this idea that whatever we start with, we have to end with. And here's our general equation: moment of inertia, angular velocity initial, moment of inertia, angular velocity final. And that if we have a large moment of inertia, that we then in a final state make smaller, then we must increase our angular velocity for these items to remain equal. And so that's why when we tuck our arms in, we start spinning faster. Okay, so that is momentum. And we are probably going to jump right into energy. So look for the guided notes for energy back on the top of the unit and get those printed out. And then our next day we'll have videos for that.